Okay, I'm going to tell you about the TempleOS compiler. So it's 20,000 lines of code. 20,000 lines of code. It has an assembler for x86 64 and an unassembler. It's strictly 64-bit for Holy C. The assembler can do 16-bit, sort of, or it doesn't have full segmentation support. I'm trying in TempleOS to keep the number of lines of code to a minimum. It's one of my highest goals. Anyway, so a normal diagram has a stream coming from the preprocessor into the lex, into the parser, into the optimizer, into the back end. This is the normal conceptual model of a compiler. So in TempleOS, okay, first of all, this does not generate intermediate files. I think my compiler is unusually fast. As a matter of fact, well, I haven't benchmarked, but anyway, so I don't do a preprocessor into a separate file. I don't do a stream either. Lex is a function called by the parser, and Lex has the preprocessor built in. So get this in your head. You have the preprocessor, the Lex. What the lexical analyzer does is it makes tokens. A token is the smallest unit of interest in the stream of compiled code. So if I have a compiled code I64I for I equals 0, I less or equal to 10, I plus plus. If I have something like this, alphanumerics are combined together into a token of an identifier. This is called an identifier. Here are all the tokens. You have, okay, I have a superscript and subscript. That's, anyway, so, if you take a compiler course, you learn about the lexical analyzer and the front end. I don't think very many places teach back-end compilers. I just had a front end. Anyway, so an identifier is a bunch of alphanumerics that make up a keyword or a label or something. That's what an identifier is. And the lexical analyzer puts together tokens, or it divides into tokens, I should say. So the lexical analyzer would say, okay, we have an identifier I64. It skips the white space. The lexical analyzer gets rid of white space and comments, and the preprocessor handles pound include. I have my lexical analyzer is merged with my preprocessor. Anyway, so I is an identifier. Then you have a semicolon, and guess what? I don't have a token for semicolon. All the symbols, or what do you want to call them? All the punctuation marks are treated by their ASCII value. So when the lexical analyzer is a function you call as you're parsing, and it says, okay, we have a token identifier, we have a token identifier I, we have a semicolon, and it returns the ASCII of the semicolon. Then it says we have a token for, which is also a keyword, and then we have then it returns the ASCII of a parenthesis. Then it says we have an identifier I. Then it returns the ASCII of the equal. So if we were going to diagram this, we'd say we have token identifier, and I have a structure for compiling control structure or something like that. Compiler control structure, and just the lexical analyzer is a function that gets one token, and it also stores the token if you want it to fetch it for later. It returns the token as the return value of the lex, and in this structure it puts the current. Oh, by the way, numbers are converted to from ASCII to binary. That's what they call it, binary. It's kind of weird calling it binary, but anyway. So I have a spot for if it's an integer, if it's a float, if it's a string. This is from an identifier. Now you can merge together multiple identifier. Never mind. So some of the other tokens are string and oops, where did the tokens go? So identifier. This is a string that comes in double quotes. An integer, a character constant, is single quotes. My compiler is unusual because I let you put multiple character constant characters. Let me just show you what I mean. If you say I64I equals quote A, B, C, D, and in normal C you can only have one character, but in here we have it makes an integer by just shifting in multiple characters. Anyway, so we can have a character constant, a float. Now for the single symbol, for the single punctuation symbols, we return the ASCII. For the multiple operators, we have some tokens for that are. So we take care of merging together two character operators, shift left, shift right, etc., etc. And you will not get the if-defs. You will not see them, but internally it sees those. And we have ... binary. Okay, so TempleOS allows sprites in source code. So if we look at our demo game, so in this source code is sprites. So the lexical analyzer has to return a pointer to a binary sprite. Okay, so I just wanted to get you familiar with the lexical analyzer returns tokens. The parser starts putting together expressions. Parsing an expression with operator precedent is the hardest part of a compiler. Conceptually, they do some when they explain it. If you take a compiler course, they'll talk about left recursive, LR parsing and stuff. Don't do that. Don't do nestle. There's one thing that's ridiculous, which is if you have there's a trick. There's a technique they teach in school for parsing expressions, and what you do is you make a recursive function for each level of operator. And I changed the operator precedence, by the way. I made bit shift exponential. So it's the highest precedence. It's a lot better. Anyway, so don't do that LR parsing. Instead, make a precedence integer that, and compare the precedence. Don't do that LR parsing. Well, if you're making just sometimes it's not important if it's good, a good compiler, fast. Anyway, so parsing, that's where you put together statements and expressions, and then optimizing. One of the main things that okay, my parser generates stack machine code. So if you give an expression like this, what it says is push 1, push 2, push 3, pop RAX, pop RDX. I don't know, I'm kind of multiply RAX times RDX, push RAX. I'm just talking conceptually. And then push 4. And then we do, oh, I skipped a step. So you push RAX. Then you say pop RAX, pop RDX, add RAX plus RDX, push RAX, push 4, and then we do the pop and add. Reverse Polish, basically. So that's the idea. I want to make an intermediate code that's my own representation of the code. So what I do is I make a stack machine intermediate code, and then in my optimization stage I substitute registers for common offsets. So the local variable, I only do stack function arguments. I don't do register arguments. The x86-64, some people like to say it has a standard for register arguments. Well, only if you want to follow it. I get people Jedi mind tricking me. Oh, you have x86-64. That means you use register arguments. No, I don't. I don't use register arguments. And I assure you it is x86-64. Anyway, so one of the things you have to know about, you have to know assembly in order to do a compiler. And the arguments are... by the time you get to a, let's see, the stack, you have to know the stack frame. I use the old school stack frame all the time. I use the RBP stack frame, and that makes it possible to climb the stack really easily. Anyway, so I don't know what I'm drawing here. Anyway, so the arguments are positive off the stack, off the base pointer. I type stuff when I'm talking and I don't pay attention. It just comes out. Anyway, so the return address of the function is at 8. The base pointer is at 0. That's because you push it. Move. You say push when you call a function. Push RBP, move RBP, RSP. Then you have your function. And then you have your. I push my any local variables that I'm preserving, and then I have my code, and you pop. Or I don't preserve all registers. I have some registers that I always trash. Anyway, pop RBP return. There's an x86 instruction called leave. And one more thing is, where do I put? I don't think it matters. You create your local variable area on the stack, and this leave. I'm not sure if I put this here or here. I forgot. Anyway, the leave cleans all of that up. So there's an enter that is slow. Anyway, so now we're ready to look at the code, and so the parser, we make intermediate code, and optimizer. See, there's these local variables that are offsets off of RBP. And what I do when I convert to registers is I just look, I say, okay, how often is this 8 off of RBP used? And in the function it's used 10 times. This one's used 5 times. So for allocating my register variables, I say, okay, we want the most common offset to be RSI. And that's how I do my allocation. I look at, anyway, so I start with the super simple stack machine, and then I take RISC and put them into CISC. I merge them together, and I convert the offsets into register variables. You know, it's funny, a lot of people say, it's not 64. I crack up laughing because my compiler it's easier with 16, 64-bit registers. Those people that did segmented 16-bit compilers, they were gods, because that's really hard to do segmentation and just having a couple registers. I guess they just, anyway. So it's 60. It doesn't do 32-bit. Anyway, so optimizing. What it does is it converts these to a stack machine, and it simplifies constants in the optimization. It simplifies constants in the optimization. And then the back end is where we convert it to machine code. We don't make assembly source. We don't make an assembler code. So in my back end, goddamn bird. So in my back end, we make machine code right in the back end, not assembly code. This is telling it to do intermediate code U24. U8 is 8-bit. U24 that's 3 bytes. U8 is 1 byte. U24 is 3 bytes. U32 is 4 bytes. Anyway, so let's start over. So we start in the electrical analyzer. The electrical analyzer has to be able to handle straight ASCII, and it also has to handle my $ documents with the sprites. So before, when it's getting started, it has straight ASCII And then later on, it can handle the documents with the $ for superscripts and subscripts. As a matter of fact, you can say the whole reason there's that nonsense in there is you can say I64H. Let's see, is it Alt P? Alt P. No, that's not what we want. Control P. Okay, H. Okay, I did the wrong thing. Control P. H. I did superscript instead of subscript. Just pretend that's a subscript. I don't. Oh, it's Alt Shift P. Okay, I'll do it. Okay. H. Alt Shift. Control Shift P. 2. Control Shift P. Oh. Okay. So you can actually have labels that have superscripts and subscripts. This is a bunch of horse manure. H2. What I mean is if it makes you happy, you can do it, but it's kind of silly, in my opinion. Anyway, so it can compile that. So the lexical analyzer combines together identifiers like I64, and what it does is it looks up in the hash table inside the lexical analyzer. Every time it has an identifier, it looks for the hash table entry, the symbol table entry. So you're already so the next stage doesn't have to search for the symbol. It's already the lexical analyzer looks in the hash table and sets off the compiler control. It sets where is that? Sets the hash entry. Off the compiler control, there's a hash entry, and there's that string. And what it does is every time you want to assign a new string, you have to free the old string. So you free the old string and then you allocate a new string. And I think I have a limit of 140 characters for identifiers. But for strings, they can be unlimited and they can include carriage returns. So as a matter of fact, you can do crazy stuff like this. Let's say U8 star name equals, then you can say quote, this is crazy. So you can then you can say print. We don't say print, but I want to just to show you. Normally we just use anyway. So this will work. See, it printed that. So you can even have. So I really went deluxe. So it converts integers. You can say 0x for hex binary. I used to have octal, but I got rid of it because I want minimum lines of code, and octal's just stupid. There was a time when it was relevant, but not anymore. So when you're doing floats, I have not verified that my floats are accurate. I don't care. So I have powers of 10. I just did it the most straightforward way. This stuff is really nasty if you want to, when you're talking about powers of 10 and powers of 2. NASA and other people do it professionally. I just get it. I get the job done, and it's efficient, and it's not that much code, because that's how we roll. So strings, string constants. That's one of the things the lexical analyzer. So the lexical analyzer will return a string constant, and the string constant. Oh, this is a character constant. The character constant. The string constants are parsed up above. Character constants are parsed here. You can have backslash characters and stuff, and backslash x. Oh, I do not do octal, backslash octal. I do not do backslash octal, except backslash 0. But I do support backslash x and then characters. So I told you the preprocessor is part of the lexical analyzer. So include, define. Define makes a symbol entry. I do not like macro functions. So there are no macro functions. Now, I started making type defs, but as it turns out, I don't have any need for type defs. One of my principles in this operating system is minimal abstraction. I decided that was one of my goals. And so I do have a type called bool, but all it is an I8. And if I were true to my principles to the extreme, I would say I8 instead of bool, but that's ridiculous. We want bool. But I almost don't use bool, just to show I'm trying to explain the concept of minimal abstraction. So I don't want function, I don't want anything you have to go look up. That's an abstraction. So I don't want abstractions. I don't want you to have to look up what a macro is. I don't want you to have, or a macro function. I don't want, I would prefer to use I6. If it's an integer, don't call it something else. Just call it an integer. I don't mess around with that size t stuff and all that. So I want minimal abstraction. So I don't have type defs. I was able to get rid of them after I found that I didn't really use them. That's just the nature of how this project worked out. Oh, by the way, the Lex calls a get char, which and it has an unget. You can unget one symbol, one character. So that makes it kind of tricky. There is a lexical push and pop. There is a lexical push and pop, and you do have to use those when you're doing like a for statement. A for statement is actually out of order, but almost everything else is straight one-to-one in order compilation. But a for statement is out of order because it kicks that. A for statement has that third term down at the. It's out of order. Anyway, so there's you can use the lexical analyzer for your own applications. I use it for, I have a reformat that redoes the spacing of the indentation, and it does a complete parsing. I do my songs with the lexical analyzer. My songs are actually code. So I use the lexical analyzer a lot, just because it's handy and it's powerful. And so you can push and pop, get char. Anyway, so the get char is that's the most time critical function in the entire compiler. This get char. It turns out that the volume of data gets smaller and smaller as you work through the stages. So the raw ASCII is like the biggest size. When it's characters, that's when it's bulky, and so that it's not that big a difference. But that phase of the compiler is the slowest, or the most time. So the get char is really nasty because it has to do those documents, and the documents are they can have sprites, they can have other stuff, and I use goto. But it's critical, so I justify it that way. It's my project. I'm the boss. I can use goto if I feel it's necessary, and I can tell you not to use it. Anyway, so get char, and it has to do the conditional compilation if def, if not def, include, if else, or just else. If so, that's a little bit tricky, but it's merged in with. There's not a separate preprocessor, and then by the same token, there's not a separate assembler stage at the end. It goes straight into machine code. So now we're ready to look at the parser. The parser has a stack. It has the output code structure, and then it has a stack that it uses for when you're doing parsing. You either handle the operator now, or you check the precedence and you handle it later. So if you handle it later, you have to store it away temporarily. And then at the next operator, you say, okay, is it time now? And then you pop. So there's a state machine for my expression parser. I didn't do LR parsing. I've done that before, but this is better. We have a precedence level, precedence that we compare. So we can go over parsing and expression. First, you handle unary, plus, minus, tilde. These are kind of the states they transition. We parse a unary term. This is kind of how an LR parser is labeled. Parse a unary term. And that's basically a unary term. Then modifiers. If you have structures, my modifiers are, you can say auto increment, auto decrement. You can say star is another unary prefix. Anyway, I should call it prefix, shouldn't I? Anyway, structure dereferencing is a modifier, is what I call it. It's not good to make up your own terminology, but that's. I probably should research to see what the standard everyone else uses. I call it a modifier. Maybe modifier. Okay, this is for. I do my typecasting post-fix. Now, is that crazy? So it was a lot easier. Some people say you make the compiler, no matter how complicated, you make it handle what's best. But what we do is you can say you, and then you say so normally typecasting is prefix. Normally you say prefix, but it's like exactly the same except it's postfix. And the way you conceptualize, I don't even know what the standard C typecasting, they got all crazy with C++, static cast and all that crap. God, they made a mess. Anyway, constant, I hate constant. Anyway, so I made my my typecasting postfix. Dereference. I want to brag about something. Is this the best time? Anyway, binary operator. So after it finishes, it has to pop everything off of its stack. This PS is the parse stack. That's this push and pop. So it pushes the. I have a the way I handle class. Okay, so I don't have a structure. I don't have structure. There is no structure keyword. There is no. I even forgot. That's pretty. I haven't used C in so long. Structure. There is no structure. There's just class. And internally, I have a parse class. When you make a new class, oh, I did a for loop. So you need to have a list of members in the class. All of these are hash table entries. All of them go into a big hash table. Anyway, so this has a list of members, which each class has a list of members. Now, the way I handle pointers, so if you have a pointer to a the way the compiler handles classes, damn it. The way the compiler handles classes is there's a structure with five copies of the class structure. So what it does is it allocates an array of 5 of these structures, identical. So they're like just tacked together. And if you have 1 star, it points to 1. If you have 2 star, it points to 2. If you have 3 star, it points to 3. And so by doing that, that's how I handle classes. So you can see how many stars you have at the moment. So you can go backward, convert either way. Anyway, so when you're parsing an expression, you have the operator that you're saving, and then you also have the class of that that expression. So let's see if we can do a pass trace. Okay. So pass 0 has these are my intermediate codes. So when we're I'm saying I equals 6 plus 6. Let's look at this. So the raw parsing, it's off the base pointer. I is a -8 off the base pointer. We want to add, so we add this immediate to the base pointer. Then we push. So we push the base pointer. Conceptually, we push the base pointer on the stack. We push this -8. We pop 2 and add and push. Then we push 6. And this size of is that because of pointer arithmetic, we have to save a spot in order. What if we're doing pointer arithmetic? And then we have to multiply. So it really made a mess. My original compiler did not do all pointer arithmetic with size 1. I kind of liked it that way. Oh well. Oh well. Anyway, it was kind of nice doing pointer arithmetic size 1 all the time. But oh well. So now we add 6 and then we have an assign, which pops. The top is what's assigned, and then pop another one, and that's where it's assigned. And this is the end of an expression. So notice here, the raw starts out like that. Then when it pass 1 simplifies that constant to a 12. So it started out as 6 and 6. And by the time we got to pass 2, it was simplified to 12. Over here, during pass, so we have pass 0, 1, and 2. We have pass 3, 4, 5. These are optimizing. They're not optional. 7, 8, 9, 10. This is when it's generating the code, the machine code. When it's generating the machine code, it loops, shortening long jumps to short jumps, and it does that. It collapses it as much as possible. Anyway, so we start with the stack machine. At about RSI is going to be used for the I variable, which is the offset 8. So it took a look and it says, okay, what should we use register variables for? And this F8 offset was the most common. So that's going to be a register variable. And so now we're going to load effective address. I don't know why we're doing it. We're going to store the 12. And that's about all. Anyway, so then at past 9, 10, 11, it generates the machine code directly. It doesn't generate an assembly file. So it tries to compress it. So it starts out with each of these intermediate codes translates to multiple instructions, and it pastes them all together. And if you're running just in time, then all it has to do is call malloc when it figures out how much, and then just paste all those together for the function. Just in time is easier than ahead of time. If you're doing ahead of time, it has to make a binary file. If you're doing just in time, it just looks in the symbol table for calls. Anyway, so the parser parse statement. Now this is where some of my magic starts happening. When you're parsing a statement, if it finds an opcode for assembly, all the opcodes are uppercase. So in the compiler directory is a opcode file. So this has the addressing modes and opcodes for x86, 64. I don't do SSE or MMX. So opcodes uppercase. So my opcodes are uppercase, and the way I do my my coding standard, nothing else is supposed to be uppercase. And so if it sees the uppercase opcode, then it kicks it into assembly. And so you can just put assembly right in the middle of your C code, and it knows it's what it is. And then the other tricky thing is when you have a string or a character constant. In TempleOS, if it encounters a string by itself, so like hello world, how about hello? I'm going to hit F5, so it printed hello. So if it finds a string by itself at the start of an expression of a statement, so you know what a statement is, right? So for is a statement, if is a statement, an expression is a statement with a semicolon. Statements are separated by semicolons or commas. You can actually say comma. Anyway, so what it does is it calls print for standard out. If it finds a, you can print character constants. Anyway, so that's the way my compiler works for the statements, parse expression. That's what we looked at with the state machine a little while ago. So so this is where we have the statement, which we can look for a for, a try, a while. Let's look at the while because it's pretty easy. So how do we parse a while? Well, the first trick is the lex is always sitting one token ahead of where you are. So currently it's on the while keyword, and so when we say lex, it goes past the while, and now it's sitting on the whatever the parenthesis for a while. You follow? Now it makes a label. We're my intermediate code has labels. I could show you that. Let's look at it. Okay, let's say I64 equals 10 while I %d Okay, so let's do a pass trace. So what it had to do in order to parse that is it had to make a label in order to do a loop, and branch if 0. So this label is identified. So each of my intermediate codes, these are stored in a circular doubly linked list, my intermediate codes, and they have a buffer for when it makes the machine code at the end. Anyway, they have a we can look at the intermediate code. Okay, boy, this is a long video. Oh, well, anyway, hold on a second. So we want to make a label, and we make the label ahead of time, and then we insert the label down here, and so the go-to gets ends up jumping to the bottom. And this is a branch back to the top for the branch if not 0, label done. And in here is a these are sometimes recursive parse expression. So that's the while expression, and then it does the statement parse statement. That's the while statement. So you can have brackets and it's a statement. So and we have a jump at the bottom to jump back to the top. So we test the we compile the expression, we test the expression, see if it's 0, and if it's 0 we jump to the done. Otherwise, and this is where we make the done label. So this is how the parsing works. Now with the for, we actually have to store the code and insert it later, because the for statement is out of order. The code is. So where were we? Let's look at intermediate. So this is an intermediate code. We have some flags. We have each one can have one data item. That's kind of like that's the label, or if it's an immediate, it's the immediate value, or if it's anyway, it has a class. Now this does that trick with the more stars, the more the more offset in the array for the type. Anyway, we record the line number because when we make a map file, it stores the we want to do symbolic debugging. So we need to record the line number that it lexed. So that's automatically handled behind the scenes when we're building these intermediate codes. So we're doing intermediate code add. So this adds an intermediate code, and what it does is it looks at the compiler control, and it gets the line number, and then it stores it. So the intermediate codes are added as part. The intermediate codes are linked, circular linked list off of the compiler control, and they have the line number. I had to do something kind of crazy. I don't make an what do you call it, AST symbolic tree. I don't make a tree because I just make my stack machine output. But it turns out I have to make a tree backward in order to resolve the types. I was not, in the early days I just had 64-bit type, but it got more complicated and I had to add backward links in my stack machine. It's kind of ugly. And there's a buffer for when it makes the machine code at the end, and then it goes through and it splices all the machine code together. So so the parser, well, I want to brag about a feature. You can have negative displacements off of your structures. if you'll notice, there's a single byte displacement, and then there's a 4-byte displacement off of there's addressing modes. And as it turns out, a normal compiler cannot use the full range of bytes because they're signed. But what I did is I said set the pointer for the structure to -128, and now you can have negative structure values. So you can actually I learned this trick at Ticketmaster. So in the first case we're using byte offsets and then 32-bit offsets. In the second case we're using byte offsets all the way. So because it's signed, yeah, it gets nasty because when you're making your pointers, you have to point them at a strange location. So it was too weird. Otherwise, I would have used it. I did not actually even. I didn't. It's so weird that I didn't use it because I don't want it to confuse people. But if you want high performance, I don't think it makes it any faster. Anyway, so my by the way, I value the way. So we're getting to the optimizing. So optimizing past 0, 1, 2. This figures out the type, and it simplifies constant expressions. So a lot of people take a look at this code and say, "Oh, you have an interpreter." No, it's not an interpreter. It has to simplify constant expressions. What did you think a compiler does? They see this, they call it bytecode. They see my stack machine intermediate code and they call it bytecode. No, that's just where it simplifies constants. So what does this do? This simplifies constants, and it figures out the type. This is some of the. So each of my intermediate codes, you kind of saw how the stack machine worked. Well, it turns out there's a conversion bit, and there's a so each intermediate code can have 2 inputs and 1 output, and like add is 2 inputs and then an output. So there's a table. I have a lot of built-in functions. They're not inline. I don't have inline functions, but I do have some built-in functions. Anyway, so there's this table for how many inputs and how many outputs. They only have one output, but you can have multiple inputs. You can have variable number of inputs too. And so there's a flag that says convert the input to input 1 to real, or to convert input 1 to float, convert input 2 to integer, convert the output to float. So there's this conversion bit you should be aware of. ICF, intermediate code flag. So let's go over the flags. The result, convert to F64. The result, convert to integer. Argument 1, convert to F64. Argument 2, convert to integer. Sometimes you always want to use floats. If it's in pass 1, it figures out whether it's integer or float, because you know how when you divide by a float, it becomes a float. Okay, so it has to work all that out in pass 1. It uses a anyway. It builds a tree backward. That's the best way I can explain it. So this is interesting. A1 first. So when you start converting offsets to registers, the stack machine is it still uses the system stack, and And when you're using the system stack, order is important. You can't change the order if you're using the stack. And it turns out the RAX is the top of stack. And let me explain this if I can. I don't know if I can explain this. So you have push 1, move RAX 2, and then so that the add instruction always does add RAX comma pop RDX, add RAX comma RDX. So I'm not explaining this very well, but as it turns out, sometimes the RAX, the top of stack, is here, and sometimes it's here, and it's convenient to change it for I think in ifs and stuff, to change the and then when you start doing that, then you have to do the order gets different. So this makes the back end complicated. All of them have to either handle, they all have to be able to switch the order of the two arguments. So if you go look at all the back end code, all the back end code has to, all of it has that A1 first. So almost all of them have a big if statement. So if A1's first, you do that. If A2's first, you do that. Anyway, so all the code has that kind of nasty thing. Now it turns out register variables. So I started with a stack machine, and one of my rules is anything that gets put into a register has to be converted to 64-bit. So if you load from memory and it's 8-bit, you convert it to 64-bit, and then all the operations are done 64-bit. So this makes for some a normal compiler, you would call this a bug, but we don't call it a bug because that's, our language is not standard. So if I say this looks like a bug, but it's not a bug. If it gets put in a register, it's converted to 64 bits. So that's how we operate. That's the language definition. Anyway, so RAX, RBX, RCX, and RDX, those can be trashed by every intermediate code. And then RSI, RDI, RBP is already used. RSI, RDI, R8, R9. These are R10, R11, R12, R13, R14, R15. So these are available for these are stack temporaries. It's kind of like I said, the RAX is the top of stack. These two are deeper, and then the rest of these are for you can trash the stack temporaries, as well as RAX, RBX, RCX, RDX, and they're not even saved for function calls. Anyway, so the rest of these are used for local variables, and I think this pass figures out. This pass analyzes the offsets, and it says the most common offset is -8 off of RBP. Therefore, we'll give that a register. There's so many registers; they almost all get put in registers, don't they? Anyway, you have to save them and push them and pop them. So the rest of these, basically, the overall idea is you want to convert from. Let's go look at an example. you want to convert from CISC to RISC, or from RISC to CISC. So it starts out bulky with a bunch of little tiny instructions, and the optimizer merges them together into CISC instructions, and that's the purpose of the optimizer. Turns out it doesn't really make it any faster because the Intel chips are just as fast with RISC. It converts them back into RISC, as a matter of fact. So we could simplify the compiler and save ourselves some trouble. Now, now some people, obviously optimizing can be done a little bit or a lot, and if you get really carried away with optimizing, it's really complicated and slow. Anyway, so I optimized like a normal assembler programmer. An average person who programs in assembly doesn't know about the pipelining, internals. So like an old school assembler, a programmer who knows old school assembly, that's kind of how I made my compiler. And I did not unroll loops. I kind of tried for minimum code size. That's kind of like, I know that's silly, but my goal is I want it to be pretty when the kids look at the assembly of a function. I want them to be able to understand it. So no extreme measures. Try to be just straightforward. So I was able to, if you look at the assembly, I think it's pretty good. I haven't benchmarked, but I don't do stuff like unrolling loops and stuff like that. Anyway, so where were we? So the most interesting thing is, so there's a big, when it steps through the intermediate code, it's always a big switch statement. And I have a no bound switch, as a matter of fact. I have I'm the only person who has no bound switch. So normally, no bound switch. This is my own. So normally a switch statement, if it's outside the range, will just skip over it, but mine will crash. I do not check for a bound, so it's a little faster. So one of the things it has to do is handle. Okay, it merges together forward. It merges together jumps. So if you jump to a jump, then it does that. It gets rid of dead code. And when it compiles, I don't have segments the way everybody else does. Everybody else has data and code segments. I don't really have that. I put my code function by function, and I put my code compiled function by function, and let's go ahead and trace this. I put my code function by function. Oops. What? Okay. So I put my code, and then after the function, I put any data. Like this is the string. 25 is the star or percent, I guess. %s. So there's the string, and so in the compiler, the main. I guess, is it main? Let's see. No, it's not it. Optimizer. Where did I put that? No. there it is. Parsley. I would not have guessed. So it calls the different passes, one per file. There's a file for each of the passes, and then the last pass loops over and over as long as it's able to shrink it more and more. So you can actually see that logic here. So while the code size is less than the last code size, we want to compile that or do that last pass. And so in the last pass, we store that extra data, like the jump table is an array for the jump table has an array. This gets stored after the function. The string constants are stored after the function. Sprites are stored after the constant. Sprites are treated just like string constants. And float constants are stored after the function. And we have to record the line number of each. You might not know this, but there's a map file. There's a map file which has hidden. It has the line numbers, and when you this is for like I told you, just in time is easier than ahead of time. There's only two ahead of time. The kernel and the compiler are ahead of time. Both of those have map files, and during boot, we load the map files. Where do we load the map files? Start OS. I think we do it at the end. In the home, make home. Plugin or packages. Yeah, we load the map files in the packages. So that's so that we have source debugging. Now for the just-in-time, it's already sitting in memory. There's no problem with just-in-time. So the last pass it has to the last pass it figures out the size, the final size, and that's when it makes the final. It's a malloc. Technically, we have a code in a data heap, but I don't want to confuse you. It's not like a linker segment in other compilers. So yeah, I'm really pissed off that the UEFI boot requires ELF files, and that is just not in our dictionary. We do not do ELF. And we are going to command the industry to take that shit out of there. We are not doing ELF. So we can look at the back end. So the 7, 8, and 9 pass has a big switch statement, and then it calls the back end for each of the. Let's take an example of. One of these back. Oh, let's just jump in here. So yeah, you have unaries and we do short circuit logic all the time. Comparison. So this is generating machine code. Some of the more common the slash operators. So there's a library of. So you store one U8, store a Rex, store U24. Add to the stack pointer modder. This is a common addressing mode. So anyway, now I have an assembler. I can tell you how the assembler works. First, let's talk about the unassembler. Basically, here's what you have to do. You have variable length instructions, and you have to come up with a way of ordering the instructions. And once you have an order, then you can do a binary search to figure out what opcode. So I have all the opcodes in a file that I load at boot, opcodes and addressing modes. And once you can order them, then you can do a binary search. It's kind of nasty, but so first of all, I sort the I make a table with the sorted opcodes, and then I do a binary search when I'm unassembling. So my unassembler, I have an unassembler, unassemble. Let's just do this. Unassemble. I'm just going to grab an address at 10,000. So there's my unassembler, and it has symbolic. So it searches the hash tables for symbols, and so it has to. Maybe you have 48 8B. So what you have to do is you have to do a binary search to see what opcode it is, move, and then once you have the opcode, it's pretty easy. So each opcode has multiple addressing modes. Like for example, the move has, well anyway, each opcode has multiple addressing modes. And now for assembling, the way that I assemble is first I load that file with all the opcodes. Then I figure out which addressing mode. Once you have an opcode, I have non-standard opcodes. You have to tell it you have a 2 operand mul or a 1 operand mul. So I disambiguated. Some people might not like that, but anyway, normal assembly, and also character turn doesn't matter in my assembly code, so you can. That's kind of silly. I won't even distract you. What you have to do is you start with the opcode, then you have to figure out which addressing mode it is, and you have to parse expressions. You have to store. Where is? Okay, here it is. So I make a. This is the heart of my assembler. So I have. These RT, these are the opcodes, or addressing modes. I'm sorry, these are the addressing modes. So I have bits for the addressing modes. So if it's relative 8, relative 16, relative 32, immediate 8, immediate 16, immediate, unsigned immediate, register, modder, memory. I don't support the segmentation. My 16-bit support is almost non-existent. All I have to do is get through the bootloader, and so I don't even support segmentation. None of that. Anyway, so I have all these addressing modes, and then by process of elimination, I say I eliminate bits until, does it have an offset? Yes or no, and then I eliminate bits in the. This is a bit mask for those addressing modes, and so based on size, we can eliminate a bunch, and then once sometimes you can have multiple addressing modes that are valid, and then it picks the one with shortest byte output. Anyway, so I hope you understood. So for so the size is the most critical. So for anyway, I think that's all I want to show you on the compiler. Let's see if I'm forgetting anything. So there's templates. when I first started, I made a template for each opcode. I spliced them together and then I patched. So if you inline each opcode, like when I first started, I had something like push 1, pop RAX, pop RDX, add RAX, RDX, push RAX. So when I first started, I had all my operators done in assembly, and then what I did is I just inlined them together. Oh, that reminds me. So I should go over how you add an inline function. So ICT, no. ICC, no. Intermediate code, Scheist. Okay. So let me show you how you add a inline function, because it doesn't do inline functions normally. Okay, so these are my intermediate codes, IC underscore. So let's look at square root, or square. Let's look at square. IC, there's square root. I have a square I64. Okay, so find SQR I64. So this is all the, so when you want to add your own inline function, then first you need a when it boots it, you have to give it a you have to bind a C function header to the intermediate code. This is an internal function. You give it the intermediate code, and then you give the C header. So that's what you need. You need the you need to add your own here. You also need to add your own in init. That's not listed, but in here you have to add your own square root. You have to add your own and tell how many arguments. And then the rest of it is just each pass has to handle that in the switch statement. So a lot of them are simple. All the functions are about the same. So this, when it finally gets to the last pass, it calls IC square in order to convert it to binary. And what is this doing? It's so the move. I should tell you what the back end, how the back end works. The back end has type mode. So this is not. This is. You can have an immediate mode. You can have a register. You can have a displacement. You can have an index register (SIB). You can have a RIP relative, or you can have stack. This is the original stack, which started as the system stack. So you normally you do it in registers, and you no longer actually use the system stack like that. So in all of these back-end routines, you'll find the parameters are type, register, displacement. That's the order. Each argument is indicated by a type, register, displacement. So you see how there's type. This is argument 1 type, argument 1 register, argument 1 displacement, argument 2 type, argument 2 register, argument 2 displacement. So the type is actually both the addressing mode and the size. It's a number. I kind of smushed together the addressing mode and the here's the raw types. So if it's a U8, U16, U32, F32, F64, we don't have F32, F64. So in all of these back-end routines, you'll see the type, which is the addressing mode, plus the size, the register if it has one, the displacement if it has one, and so that's how we have to pass it to all these routines. Anyway, so it does. There are some library routines. You'll see those in back-end library. These are the floating point back-end. So the final thing it has to do is make the binary files, and what we do is you can go to my web page and you can get binrep. This has the binary file format. So if it's just in time, it's really easy. If it's ahead of time, I'm going to dump the binary file, binrep compiler. So this has a relative export table with relative import table. So it has to import all these symbols and patch all these addresses, and it has to docmax. I don't want a limit on my command line buffer. So at the top is we have exports and imports. Oh, here's the all my code is position independent. There's a table for every single absolute address. My binary files are kind of bloated, you could say. Not really. Anyway, there's this table for all the absolute addresses that need to be patched, and that enables all my code to be quote unquote position independent. But that's because it's patched at load time. And here's the exports, relative 32 export, and here's the imports. That's all there is to it.